Yeah,
Great. So can we see this?
yeah, we can see your slides and you have 15 minutes.
Great. Okay, so this is a presentation on using low PT tracking for Atlas and nominal LHC pileup. So a little bit on the current status of Atlas tracking. We attempt to reconstruct particles with, well, charged particles with PT down to 500 MeV. However, as the plot on the right shows, particles from pileup interactions and from the underlying events of high Q-squared proton-proton collisions at the LHC are actually most likely to have PT below 500 MeV. Of course, for most analyses, these particles are not particularly interesting, and reconstructing these tracks has a steep cost in terms of time and storage. So why would you want to reconstruct low PT tracks? There are analyses where this information can be useful. I have a few listed on this slide. Just for an example, if you are doing a search for photon-induced physics, you can use better reconstruction of an underlying event to help distinguish between photon and parton-induced interactions. In the past, Atlas has reconstructed tracks with PT down to 100 MeV, but this was done in low pileup conditions, and you can see a plot of the efficiency that was achieved as a function of track PT on the right. Now, in order for an analysis to use low PT tracks in nominal data taking conditions, you need the implementation to work in conditions where you have up to, say, 70 proton-proton collisions per crossing, as opposed to 1. So the main challenge that comes along with high pileup, of course, for us, is a large multiplicity of hits within the Atlas inner detector. So in Atlas, tracks are formed from seeds, and the seeds themselves are formed from combinations of 3 layers of hits. So either 3 pixel layer hits or 3 SCT hits, and occasionally an extra confirmation hit. High PT charged particles curve relatively little in the magnetic field, so seed finding is more or less a question of finding 3 hits that form a line in space or small deviations from a line. But as you open yourself up to lower and lower PT, a larger and larger amount of phase space opens up, and now you can find significantly nonlinear combinations of hits, resulting in a large combinatorics problem. So in order to mitigate this problem, what we're going to do is run tracking in 2 passes. First, we do the nominal tracking, then you remove the hits that are used by these tracks, and then you perform a second pass using the leftover hits as input. And you also have slightly relaxed hit requirements for the low PT tracks. An additional trick that we use to reduce the combinatorics is to use what we call the region of interest. The position of this region of interest is chosen from reconstructed objects in data or Monte Carlo, or perhaps from a truth level position in Monte Carlo. So say you have some dimuon event, you can choose that as the location of the region of interest. And what you do is you iteratively find the seeds in the event and then reject the seeds if they are pointing away from this region of interest. And then only for the successful seeds, i.e. the ones that are pointing into the region of interest, do you actually extend the seed into a candidate and move on to the ambiguity solving process, which we do. And the ROI size is configurable, and the choice of this size will be explored in the coming slides. A little illustration is shown on the bottom of this slide. The red horizontal line can be taken to be the beam line. Interactions can occur over a large distance of this line, including outside of the region of interest, which is shown in green. So if the seeds point into the green region, then they will get passed on to the next stages of tracking. And that is as far as the algorithm goes. I have highlighted in blue a sub-region of the region of interest. This is not part of the algorithm, but it is important for actual analysis. I'm calling this the window of interest, so to speak. This is the region that's immediately surrounding the hard scatter, because really you don't necessarily care about low PT tracks that are 15 millimeters away from the hardscatter. What you really care about is tracks that are within, say, 1 millimeter of the hardscatter. So most of the plots that I'll show about efficiency and fake rate correspond to a subset of the region of interest. So in terms of evaluating the performance of our algorithm, there are three key things. The first, of course, is efficiency. This is just going to be the number of charged particles with at least one reconstructed track divided by the number of charged particles. The second thing would be the fake rate. So a fake track is one that is constructed from detector hits that are created by just multiple different charged particles, which is to say that it is a track that does not correspond to a truth level object trajectory. And lastly, we of course care about the reconstruction time. So the question is just how much longer does the reconstruction take when you're using the low PT tracking? So we will use these metrics to determine an optimal region of interest size and to evaluate the performance of the algorithm in general. So in terms of determining the ROI size, on the left, we have plotted the efficiency and the fake rate as a function of the region of interest size. You see that for a very small region of interest, say 2 or 10 millimeters, the efficiency tends to be low for different track PTs, and the fake rate tends to be high. The efficiency seems to peak at around 30 millimeters, and the fake rate also tends to die off with a larger region of interest size. On the right, you see the time impact. So you can see for a region of interest size of about 30 millimeters, the total reconstruction time, which is depicted in the black, is roughly doubled, and the tracking time alone, which is shown in the blue, is basically quadrupled at the region of interest of 30. So given the previous two plots, we see that a small region of interest, while it is fast, it generally has low efficiency and high fakes. A large region of interest has low fakes, slightly lower efficiency than maximal, but it tends to be time intensive. And a medium region of interest has close to maximal efficiency at the cost of medium fakes and a moderate reconstruction time impact. So what we have done is adopt 30 millimeters as a tentative default, but of course it's an adjustable parameter when you call the algorithm. So another key thing to consider for us, basically the key point of the algorithm, is how do efficiency and fake rate perform as a function of PT now? So on the left here, we have the efficiency plotted as a function of the truth particle PT. The nominal tracking is shown in the black line. You see, of course, that it dies off around 500 MeV, as it is supposed to. The blue points show what efficiency you achieve when you run with the low PT tracking. It's nice to see that you get a relatively smooth efficiency that stays above about 80%, down to around 200 MeV, with a quick die-off after that. So the efficiency becomes very poor, below around 200 MeV. And on the right, you see the fake rate for the low PT and default tracks combined. You see for the very low PT regime, again, you have a very high fake rate. About 1 in 3 tracks are actually fake. However, above about 250 MeV, the fake rate is below 10%, which is pretty decent. So given the problems that we see in the very low PT regime, the key question that we would ask is, how can we improve the efficiency and or decrease the fake rate? So just as a quick reminder, Atlas tracking is performed in 3 stages. First, we create the seeds, which I've already briefly talked about, from 3 space points. Then you extend the seeds through additional hits using a Kalman filter to create candidates, and there might be multiple candidates per truth particle. So then you move on to the ambiguity solving, where you essentially filter down your set of candidates and hopefully remain with 1 track per particle. So things go in there like not too much hit sharing, etc. So in order to increase efficiency, you would either want more seeds or perhaps looser ambiguity solving. And to decrease fake rate, what you would want is fewer seeds probably, or perhaps tighter ambiguity solving. So first, let's examine where the efficiency is actually being lost and also look at the seed quality. So where is efficiency being lost? To address that question, we have on the right a plot of the efficiency for seeding, for candidates, and for tracks. The black points are the same as those shown a few slides ago. What you can understand from the red points, which is the seeding efficiency, is that most particles have at least one seed linked to them at truth particle, or at truth level, which means that of the hits in the seed, it contributes the most energy, more or less. So about half of the seed to track lost is lost in the candidate stage, above about 200 MeV. So there seems to be a relatively consistent loss in efficiency going from seeds to candidates to tracks in the higher PT regime. But given the fact that we have typically at least one seed per particle, does this mean that we should just accept a higher fraction of the seeds to increase our efficiency? Because remember, you can see from here that we have a very large drop from seed to candidate, especially at very low PT. So in order to address that question, what we're going to use as a metric for seed quality is quote unquote truth match probability. This is basically a weighted fraction of hits on a track created by the same truth particle. So remembering that seeds are typically formed from hits on 3 layers, if all 3 of the hits are from different truth particles, that means the truth match probability is going to be 1/3. It's a truly random seed. So typically we would consider a seed fake if fewer than half of the hits come from the same particle. So a little illustration of this is on the bottom. On the very left, here you see a good track where all 3 of the hits come from the same charged particle. In the middle, where 2 of the 3 hits come from the same particle. And this is also not considered fake. But on the right, this is a truly fake seed where all 3 of the hits that comprised the seed came from different charged particles. So looking at the fraction of true and fake seeds as a function of the seed PT estimate, where the PT estimate is just basically formed by drawing a circle through the 3 hits that comprise the seed. What we find is that at very low PT estimate, almost 45%, or basically half of the seeds, are just random combinations of hits. So when truth match probability is very low like that, you actually don't necessarily expect the seed to be able to be properly extended through hits on other layers. So finding a large drop from seed to candidate isn't actually very unexpected here, given the poor seed quality. And if you loosen the selection requirements, basically all you're going to do is increase this already poor fake rate for the seeds. Now, that means that improving the efficiency, especially at very low PT, is going to be challenging. But another thing that you would want to do for the algorithm in general is to decrease the fake rate. And so in order to do that, what you would want to do is tighten the seed to candidate to track selections. But of course, you need enough seeds per track to even consider doing this. So if there was only one good seed per track, if you started really restricting what seeds get passed along the algorithm, your efficiency is going to drop. So on the right-hand side, for tracks that end up getting selected, we have a plot of the seeds that are the difference in the longitudinal position of the seeds that get linked to the track versus the longitudinal position of the track itself, for those coming from the low PT tracking pass, of course. So we see here that fake seeds that end up getting linked to the track can typically point almost anywhere. This isn't unexpected because the fake seeds are just random combinations of hits. But we do see that low PT tracks typically have around 2 good seeds pointing within 5 millimeter of them along the beamline. So given that seed resolution plot on the previous slide, let's restrict ourselves to looking at the seeds within 5 millimeters of the tracks and consider the number of seeds per track as a function of the PT of the truth particles to which the tracks eventually get linked. So how many of such seeds do we see per track? Typically we see about 2 seeds per track, and this doesn't seem to have a very large PT dependence except for the very, very low PT bin of say 50 to 100. So given this, that we have about 2 seeds per track, maybe this means that there is a little wiggle room for reducing fake rate here. There's a little bit of redundancy in seeds per track, which is good. So for moving forward with this algorithm, it looks like increasing the efficiency for very low PT particles is somewhat difficult. There's a large combinatorial background, and almost half of our seeds are just hits of random origin being combined. And relaxing seeding selections makes that worse, of course. So reducing the fake rate might be possible by tightening selections. And there are a couple of options here. You could do this at reconstruction level, and this actually might have the benefit of reducing reconstruction time. Or alternatively, you can do this offline at track level. So you make some set of track selections based on track PT, pseudo rapidity, the number of hits, et cetera, et cetera. And such a selection can, of course, decrease fake rate, but it will naturally have a negative effect on efficiency because you only have a final set of tracks. And if you start taking away tracks, that cannot possibly improve efficiency. Of course, striking a balance between fake rate and efficiency is somewhat of an analysis-specific question. So in conclusion, low PT tracking can be a useful tool for many analyses for Atlas, and we have created a framework that can be applied to specific events of interest for analyses, and it's a very portable framework. Overall, extending tracking down to around 200 MeV can actually be done in generic run-to pileup with relatively high efficiency and a low fake rate. In the very low PT regime, though, say below 200 or 250 MeV, the fake rate does tend to become significant, but we think that this can be mitigated with offline selections. Of course, the impact on reconstruction time is not totally negligible, but there is room for improvement by tightening seed selection criteria, as I discussed on the previous slide. So that's the end of this talk. However, I'll just point out, for the sake of the recording, that in backup, I have here a slide where you can directly compare the min bias, so the very low pileup efficiency, to the efficiency that we're getting in high pileup, and then a few slides with text and cartoons explaining some of the performance metrics versus the region of interest size, which might be something that you had questions about if you were just looking through the slides. So, thank you.
All right, thank you very much, Patrick. Very interesting. So let me open for maybe one or two quick questions. So I see people using for the first time, or at least I see it for the first time, the raising hands. So yes, please go ahead, Giantonio.
Hi. First of all, thank you very much for the very nice report you've been giving. And I would actually want to make a question and a comment. So for those, we know that for low PT particles, like below a few hundreds of MeV, actually we deal sometimes, most of the time, if they're not electrons, with particles with a beta which is not equal to 1. So we expect like huge variations, for example, in the E over dx compared to minimum ionizing particles, and also multiple scattering actually matters quite a lot, because also for the case of the muon, like we know that multiple scattering of a muon at 100 MeV is much different from a muon at 1 GeV, right? So I was wondering, A, if you take these, you make some assumptions on these to take advantage of this information, and B, if, for example, for the case of the electrons, you have a similar plot of the efficiency as a function of the APT, because you use it Z to mu mu, right? So I was wondering if for the electrons, which is at beta equal to 1, even at those low PT, if the situation is better or not. Thanks.
Right. So there actually aren't any particular assumptions or additional informations that get put into the algorithm beyond the sort of generic tracking. Looking at the DEDX is actually something that could be done for making track selections. Putting that into the actual tracking might have a little bit of an extra impact on the tracking time, but sort of an idea that we would have had for some sort of offline selection is maybe developing some sort of multivariate analysis, like BDT thing, where you seed in, or you add in the hit information like DEDX. But yeah, so right now, basically all we're doing is just using sort of generic tracking algorithms. So yeah, we haven't really extended it like that.
So may I quickly comment on that?
Yes.
So the scattering regime at 100 MeV is still reasonably well Gaussian, well, it's actually well Gaussian, and so that is taken into account by just the modified Highland formula. The EDX has left has not reached the plateau yet, so that's not even very easily to describe. So I agree there is some handle a posteriori though, not in the track, not very easily in the track finding stage.
Right. Yeah, definitely is something that could be used offline, for sure.
Yeah, my question was really like, as the multiple scattering is much larger, so maybe one could widen a little bit the search window using the track search algorithm, because it is expected to have much more multiple scattering compared to the other IPT tracks.
That is happening. That is happening due to a rather simplified model in the pattern recognition. So that the window adapts to the curvature times scattering component.
Thank you.
All right. Maybe one more additional quick question, if someone has one. If I don't see the raised hand, please just shout out. If not, then thank you, Patrick.
All right,
And
thank you very much.
We'll move to the last talk.